much for the invitation. It's a great pleasure, of course, to be here. Yeah, so I will talk about my very limited experience with the partition regularity questions, actually, namely partition regularity of quadratics. Most of the audience actually know much more about these questions than I do. But nevertheless, so okay, so let me just mention one word that to set up the scene, that partition regularity in general, the linear case, the prototypical example of partition regularity questions, if I partition set of integers into k colors or k cells, then the simplest, I guess, example is the result of Schur, the first example. It says that I can always find three numbers in one color that are they add up x plus y equals 2. So I will call this equations partition. So as far as the linear case is concerned, everything is rather well, I guess, understood. And Rado essentially gave us the criterion for all linear systems. So I will not state it, by all linear equations we understand very well. So just the goal of this talk is I want to show you somehow that these questions that we know about partition regularity are very sensitive to coefficients. And you switch one coefficient, and at least these methods, in some cases they can say a lot, and in some cases they can say absolutely nothing. So let me just quickly jump to the nonlinear case. And here, so nonlinear. Well, the simplest I can do with this example is to make one of them square. And this is a famous, so equation x minus y equals to n squared. And here I allow x and y to be of the same color and n be arbitrary. This is a famous theorem of Furstenberg and Sarkozy. I will abbreviate from now on the names, because I'm not just meant to. But Furstenberg and Sarkozy, they proved that we can always find two numbers in one cell, and the third number can be anything, such that you can find the monochromatic solution to such equations. So, well, the next nonlinear simplest case, in some sense, whether this can be made to be also from the same cell, and this was shortly after proved by Bergerson, that one can put the third one in the same color as well. But well, what else can I do with this equation? Well, I can put x plus y equals to n squared, and that so again I want to find two monochromatic, and one I can have anything, and this is there was a conjecture, I think, of Erdős, and that was solved maybe mid-2000s by Kafalak and Semereri, who showed that actually this equation is particular in this form. And again, m can be anything. The situation, well, I mean, I can try to upgrade it to all three line in the same cell, and here the situation is interesting. So in general, this is not partition regular, which was, I guess, first proven the example by Tsvitskaya, Garamati, and Sarkozy. But so not partition regular. But so for two colors, yes, for two colors. And there were two proofs, I think. So one is by Ben and Sophia Lindquist, so Corinne Lindquist, and also simplified version by Peter Park, I think. The audience maybe not. So you can see that there is a difference which is going on here. So, okay, this is like next stage of nonlinearity. I can put square here, for instance. And this equation was proved to be partition regular. Yes. And this is breakthrough of Joel. in sequence of the work we've heard before in this concept. So this is next stage of nonlinearity. Okay, I guess we have no other options but to move to 3 squares. I have no other room. And this equation is, well, we've already heard about that. And the only thing we know, it is expected to be partition regular for all 3 variables. But the only thing that we know right now is this work that Joel mentioned already, yes, for 2 colors. Essentially, the way it was proved is that they just showed that everything, if you color everything from 1 to 7,000, then no matter how you color for 2 colors, you can find the monochromatic triangle. So this is the work of Hule, Klurman, and Marek. So it is completely open for 3 and more colors. And again, as was pointed out before, that Redzikinakis and Host, like about 10 years ago, they started attacking a simpler question. Of course, we don't understand triples for any equation, essentially. And to relax this condition and in the style of theorem of Semeredi and Furstenberger-Sarkozy, and try to find monochromatic pairs. So a theorem that I want to talk about today is with Nikos and Joel, is the following. So suppose I give you 3 integers. I look at the equation. Then if one of the quantities AC or BC is a square, then, well, let me call this equation star. Every time I write star, let's assume that I'm referring to this equation, then star is partition regular with respect to variables x and y. So I am allowing, I can find monochromatic x and y, but z can be of any color. So just to understand like how far we are from the truth, so let me just say that corollary of this, perhaps. So corollary of this, of course, if you take A, B, and C to be equal to 1, then you get that star if then a star is partition regular with respect to all the 3 pairs, x, y, y, z, and x, z. So this is partition regularity of Pythagorean pairs. Another corollary, let me mention, so the equation which specifically was in the literature is with the coefficient when A 1, 1, and 2, but just whatever we had in the problem session yesterday. So let's say you have equation ax squared plus by squared equals to az squared, which Sean mentioned yesterday. And the corollary of this theorem would be that it is partition regular with respect to xy and yz. But I don't know, for instance, about the partition regularity of x and z. So this theorem wouldn't apply. Okay. So this is the theorem that I want to talk to you about a little bit. So the guiding conjecture here, it's somewhat difficult to make conjectures in this field, but at least to me. But the guiding conjecture here, so we put it in writing before, but then after that, people tell me that it's been, so people that thought about partition regularity had something similar, so I won't attribute to anyone, but if AC, BC, or C times A plus B is a square, then star is partition regular with respect to xy. So this is sort of the guiding conjecture here. This for the necessary, I'm not claiming that this is a necessary that this is sufficient condition actually, well, or necessary condition. But so what we do know is something along these lines. So if star is partition regular with respect to xy, then necessarily one of AC, BC, C times A plus B, or ABC, A plus B. So this is, and one can actually show also, I just mentioned that, but that one can show that having this be in a square only is not enough to be partition regular. So there are examples. Okay, so what I want to do.
All the failures of partition regularity coming from local constructions is finite number residue classes or something.
Right. Yeah. So it does, yes. So I will talk about that. Yeah. Okay. So what I want to describe to you is the approach, which was pioneered by Pradzikinakis and Horst, the roadmap to the proof. Yeah, it doesn't fail actually. You might have the solutions modulo like locally, but you still might not be actually partition regular. But okay, so the roadmap to the proof is the following. Okay, so since this is sort of connected to ergodic theory, the starting point is Wustenberg correspondence principle. So I'll state it in the simpler. It's already appeared in Florian's talk and in Joel's talk. But so the point is that if I have a dense set in any type of density, if I have a dense set of integers, and I would want to understand how it self-intersects itself, then if I want to understand how it reaches those self-intersections under shifts, I can always find a model and a measure theoretic model of this set. Namely, I can find a space and a Borel sigma algebra. I can find a bounded measure and the measure preserving transformation and the set A with the same measure as the density. T is measure preserving. Such that if I want to understand this intersection, this can be lower bounded by the frequency of returning to my set after times. If you are not a ergodic theorist like me, you can ignore this. I won't use it much, but I want to state it. So this principle is good to prove actually density regularity questions. And the problem with our equation, so let me focus for the proof only on the equation. This Pythagoras equation, not the general one. So we do know, let me use Z variables, we recall the parameterization of this. We have a very nice parameterization. And so the problem is that if we want to use this correspondence principle to this equation, it's not really density regular under additive density notion. And this is very easy to see. If you take x and y to be 1 with 3, then there is a local abstraction that they will never add up to square. So using this as a dense model is not a good thing. And this is because this equation is not additively rich, but rather it's multiplicatively rich. So I can always multiply that, and this is dilation invariant. So that seemed to be like a wrong notion of density, and in order to define the right notion of density, well, we already heard that also in ergodic theoretic talks, that we would like to find some multiplicative notion of density. So let me just make one definition for this talk. And so phi k, this is a Foner sequence. So if it is approximately dilation invariant. So namely, no matter which integer I take and dilate it multiplicatively, I almost occupy the same set, entire set. So one particular example of Foner sequence to keep in mind that we're going to be using, and it's a good sequence to keep in mind. So you can take O primes to some k and raise them to the huge powers. So this is a nice Foner sequence, which is certainly dilation invariant because all the integers start being divisible by x, starting from some point. So this is multiplicatively rich set, and of course I can, with no problem, define my density with respect to some Foner sequence as being, well, in any kind of, let's say, frame soup. Of how much I intersect. How much of this Foner sequence I have. And so if I can say that the set has positive density, if this is right. So with this notion of density, it removes these local abstractions, and so I might expect to prove a density regularity, and this is exactly what I want to do. So I'd like to show that if I have a E, which is a natural numbers, which has positive density with respect to any Foner sequence, well, some Foner sequence, then I can always find x and y, or y and z, such that x squared, actually, let's say xy, is that. But this is a positive density. Okay. So what is the next reduction? So now I'd like to apply the Furstenberg correspondence principle, but now not for the additive action, but for this multiplicative action, because I care about the multiplication. So what is my goal now? Well, you can believe me. So my goal now becomes the following. If you rewrite it in ergodic theoretic terms, that I again end up having a space with the matter with Borel sigma algebra. And now with the action on integers, which is a multiplicative action, measure preserving multiplicative action. So again, it preserves the measures. And the action is multiplicative. And I've got my set of positive measure after I apply correspondence principle. Yeah, actually, you can obviously extend this to the rationals in a natural way. And so what I want to really understand, like in this version of Furstenberg correspondence principle, I would like to show that I return to my set let's say 1. So I would like to return to my set of the times that are given by the parameterization of Pythagoras. So again, so what I want to find, I want to prove that there exist numbers m and n and l such that I return to my set after this times. Okay. By the way, any questions so far? It seems to be a tradition to ask whether there is questions, so why not? Okay. Right. So what I want to do right now is, so I rewrote this problem in these terms, and now, so what I want to do is I want to give an interpretation of, it would be good for us to understand what does this mean really? What does this return in times mean? So there is a classical, it's also been mentioned before, there is a classical theorem of, I guess some people attribute it to Buchner, some Herglutz, that actually this corresponds, so this is Fourier, this corresponds to the Fourier coefficients of the measure on the dual group. So I can represent this as a integral Fourier coefficient of some measure, which I'll describe, on the dual group. And I should integrate here a character in this group. So people that are used to the additive action, we know that such things have an interpretation where you put your exponentials, because those are characters of additive group. So in this case, what is the dual group to the rational? So we are working with rationals here. So the dual group of rationals, these are functions, these are characters, these are functions that preserve multiplications. So these are functions from, say, natural numbers to sphere, well, such that they preserve multiplications. And of course, you can extend it to rationals in an obvious way, but then so these functions are called completely multiplicative functions, and we've seen the examples of that being Liouville or Möbius function or other functions that Yoni talked about. So this is a dual group, and so this corresponds to the Fourier coefficient of this measure. So being like, and sigma f is a bounded Borel measure. On the set of multiplicative functions.
Sigma of f.
Sigma. Well, that's what you mean? Oh yeah.
You have two f's maybe.
Yeah. Yeah. So now what I want to prove is something along the following lines. So we already made this interpretation. So in order to understand these types, I need to understand these type of gadgets. Okay. So how do I want to understand these type of gadgets? what I want to prove is the following theorem. So if sigma is bounded by L, and so what do I know about this measure? Well, one thing what I know about this measure is if that if m equals to n, for instance, that's got a intersection that's got the just interpretation of measure of A. I do know that this is positive. So I know that this measure charges positive mass, sort of zero Fourier coefficient. I know that the charge is positive mass to function 1. And I know that no matter which numbers R and S I take, because that comes from these type of measures, I know that this is non-negative. Because of this interpretation. So what I want to show is that if I take my integrals over the return in times, the partitions, if I plug in my parameterizations, so what I want to show is that these type of integrals, what would be enough to show is that if I take these type of gadgets and I average it out over the boxes. Now put here a star because this is important. This is not really what we take as an average because you have to be careful what you take. But if you average it over the lattice or a sublattice, if I can show that this lim inch when n goes to infinity is positive, then I prove that there is a return in times that correspond to the partition regularity pairs. Okay. Okay. So I need to understand quantities of this sort, this type of averages. Okay, I won't talk about the details of that, but if we think about that, so I have an integral over the group. So if I want to understand like integral over some group, so what we, at least in analytic number theory, one does is uses some type of circle method. So you want some type of circle method. Or you might want to hope for it. So if you want to use the circle method, you need to understand what is your major arcs and which gives you the main contribution, and what is your minor arc. So and for this, so for major arcs, well, let's just forget about one of these guys. And so the natural question to ask here is that when is the average of one function? Forget about everything. So suppose I have, let's say, f from n to complex numbers, and I want to understand when such averages are non-zero. So Halash already, in the end of 60s, Halash already told us when it happens. There is a theorem of Halash which says that these averages, double stars, they converge to zero unless they don't. And to understand the abstraction, of course, if you take a function f, which is all the time equals to 1, there is no way it will converge to 0. So there is no way it is a sort of doesn't give you contribution. So one abstraction is these functions which are close to 1. And there is another abstraction which comes from our favorite function n to the it. Sorry? Yeah. This is multiplicative. Did I put here? Yes. Everything. I don't talk about other functions. Do they exist actually? Uh, Even I will do make my life even easier. I say completely multiplicative. Although it completely multiplicative. Yeah, so and this function n to the IT is also a completely multiplicative function. And what happens with this average is that it actually, it doesn't exist. There is no limit, but it's sort of equal to n to the IT to over 1 plus IT roughly. So it keeps rotating around the circle. So of course, if my function f is close to this, then you might also get some mean values that are not zero. So Halash told us that these averages actually go to zero unless f is close to n to the IT in a very precise sense. So if you average over primes of this strangely looking quantity, then this might not go to zero. So f is close to p to the IT at many points. Okay, so at least we know that if we forget about this and pretend that here we just have f of n, there is some functions that might give us like positive contribution. They don't actually vanish the averages. So I guess the next step is to try to understand what happens is if you say if when does the correlations. So now let's just pretend that we have like two phases here. So what happens if when do these averages go to zero? Again, I'm here working just with one variable just to show the idea. So when does this go to zero? Or doesn't contribute? And here is, I won't put any name here because what I'm going to say is it's rather philosophy, at least in this formulation. So the philosophy says that, let me just conjugate. We already know that there is one obstructions. So philosophy says that this quantities they do go to zero unless, so what are our obstructions here? So one obstruction, of course, again, this function n to the IT. Because if I have an n to the IT and n plus 1 to the IT, they will point to direction 1. So nothing good will happen. But the second obstruction, so if f is close to the n to the IT, then there is obstruction to that. And the other obstruction, of course, if the periodicity obstruction. So I put here a character, there is some additive correlation. So unless f is close to these like kind of gadgets, then you expect it to not to contribute anything when you take the averages. And I need to define what close mean. So something that will measure closeness. And here the definition is that there is a distance, which is due to Granville and sound, distance between two multiplicative functions at scale x, square of the distance. This is this similarly looking quantity that we've seen before. So
Oleksiy,
yes,
when you put the chi there, is chi, you mean f of n plus h? And chi is like a character of.
yeah. So if here I had, you mean here? Yeah. So if I had like say n plus 3 here, and I had a character mod 3.
Okay.
So there would be a perfect correlation. And if I twist character by a little bit, I also have non-zero correlation. Any other questions? Okay, so this is the measure which measures closeness, and Granville Sound called that in their terminology, F pretends to be G. if this distance is small. So now that tells me if I follow this like circle method heuristic, then what I want to do is I want to decompose my M into major arcs, into minor arcs, which we call aperiodic functions, and you've already seen them, and something which is, well, periodic or pretentious functions. So yeah, I'm a little bit like simplifying the partition, but the aperiodic and the major arc here, at least from these two philosophies. By the way, I have to mention that this is as stated, it is a philosophy that unless this happens, but progress has been made, like spectacular progress actually, in the recent 10 years in the logarithmic Elliott conjectures and due to work of mathematics Reservio, Terry, like Ioni and other people. So so we are getting closer to this philosophy of being, maybe put some names as a theory. But as stated, it is only a philosophy. So what is the major arcs from this philosophy? Those are functions f that there exists a t and the character, the universal character, such that the distance between f and n to the it chi is smaller than infinity. I mean, in practice, you have to be a bit careful here, but just in the first approximation, say that this is them. Okay? So these are functions that are close to the. Okay, so now I will state two theorems about how we handle the major and the minor arc. So the idea is, of course, to prove that on the minor arcs, these averages converge to zero, and then the major arcs, you converge to something which is positive. Okay, so the minor arc So the minor arc, these are functions that do not pretend to be n to the it times chi, so they're far from the characters, and they're called aperiodic. So here is the theorem. So this is due to Fratsikinakis and Host, this 2013-2017 paper that we've seen over the years, and in the full generality right now with some extra addition by us. So suppose I give you a bunch of multiplicative functions. So they're multiplicative. And let's say F1 is aperiodic. And again, aperiodic just means that there is no character such that this happens. So if F1 is aperiodic, and suppose I'm giving myself linear forms of two variables, that a pair is linearly independent. And suppose that the last one, as you can see, if I want to handle such pairs, I do really need to handle also quadratic equation. So suppose that the last one is irreducible, any irreducible quadratic. This is what actually is new here compared to this one. So any irreducible quadratic. Then the averages go to zero as expected. So if I average myself out of these correlations, takes time to run. And the last one being evaluated on the quadratic, then these averages go to zero. So in the case of for Pythagorean equation, you really Frederick-Knox's host would be enough. But if you want to handle general equation with ax squared, by squared, and cz squared, you need this theorem for every quadratic, which corresponds both to imaginary and real quadratic fields. And for the real quadratic fields, when you're working with quadratic forms, there is a problem with the units there that you need to take into account. I will talk a little bit about that maybe if I have time. But this type of thing will handle the minor arc as a going to zero. So what is the major arc? So the major arc is we need to handle the functions which look something like character times n to the it and somehow find this positive contribution to the major arc. So this is a theorem which, let me actually state it in the special form, which one can call it concentration inequalities. So the concentration inequalities are the following. So suppose I'm giving you a function. So suppose f is in major arcs. Let me state it in the special form, a real valued. It's a bit more complicated for non-real valued. Then for any u naught, for any epsilon bigger than zero, there exists a q naught that as soon as q naught divides some q, the values of my binary forms they concentrate. So what do you expect here? So really what you expect is if the function f is being close to, let's say, n to the it times chi, so once you remove, it's similar to the W trick. Once you remove using these q's, the contribution of the small primes, you expect that your function concentrates around the values a squared plus db squared. So you expect your function to concentrate around this value. But this is actually smaller than epsilon when you let n go to infinity. So one more time, if these functions f, which pretend to be, this is a crucial concentration estimate that allows you to say that for many pairs m and n, you are around this value. So in particular, if a is say 1 and b is 0, you can think that these type of forms, qn plus 1 and qm, they concentrate around value f of 1, and which is actually value 1. So it is kind of important. There is actually in the proof, if you want to use it, we need to handle not just the real valued function, but you need to handle functions which are complex values. So there are some extra factors appearing here coming from the Euler products. So I need to, yeah, what essentially one needs to use is the fact it's very important, the shape of what you get here, because you need to evaluate these integrals uniformly. We know nothing about where this measure concentrates, and that's actually what gives you a problem. So it can be supported on any functions, and if you want to handle that uniformly. So the what is important is the shape of this error term. So what is important here, and I won't talk about this technicalities here, but it is important that if for this Follner sequence that I've written, that the error terms, so this Follner sequence, I allow my primes, my powers to grow to infinity, but the error term actually do not depend on that. So they actually fix, they only depend on the given Q naught. So that allows extra averaging over Qs, and that allows to pick up really the major, to make sure that the major arcs are only concentrated around function one. Because otherwise there is this problems with the Qs and with the uniformity. So it is kind of important, the shapes of the error terms of this concentration estimates and the shapes of this or the products for the error. But on the model, sort of moral of the story is what I've written. This handles these two things. Okay, so there is, let me just say a word about that because I don't really have time. I want to mention one more thing before I conclude. So for this theorem, the input really, what one needs to, for this theorem is that the heavy lift in the first attempt to attack these problems, Fritzsche-Kinakis was developed huge machinery, in particularly structural theorems for multiplicative functions, the Glover's uniform and structured and the random side. And the difference here, they already handled these type of correlation formulas where you're dealing with the quadratic forms that correspond to the imaginary quadratic fields, because there is no units. And the proof of this theorem goes through the Katai orthogonality, Katai-Debussy Katai orthogonality principle. So the key thing being that whenever you have the key thing, which I should say, let me just maybe in 3 words for those who hasn't seen that. So the key thing of using Katai orthogonality principle, Debussy Katai, which Florian talked about yesterday, is to regard this function as a multiplicative function, but in the ring of integers when I adjoin root d to that, minus root d. So this is a multiplicative function because this is norm-form. This becomes a multiplicative function in this kind of extension. So you can think of that as being a multiplicative sum and try to use the Katai orthogonality principle, which will show that these expressions controlled by the Gowers norm of f. And since they're controlled by the Gowers norm of f, Fritzsche-Kinakis host already proved that for aperiodic functions, the Gowers norms of f do go to 0. So the new thing here is that Katai orthogonality criteria for real quadratic fields where there are units, that becomes more tricky, but there is a version that one can adapt to that. And that in particular would be needed for attacking like Sean's question for x squared, say, plus 2y squared equals to z squared. You would need this extension for the real quadratic fields. Okay, so let me just mention one thing before I conclude. So I don't get into details of these things, but at least hopefully you get an idea of this approach. I just want to mention something that we need to be cautious about. The speculation. So these theorems are intimately connected to questions that Yoni talked about, namely mean convergence of ergodic averages. And in particular, so one may ask, we saw the additive actions in the previous talk, but one may ask, like, which rational functions, this is essentially equivalent, understanding these averages is essentially equivalent to the questions of which rational functions are good for L2 convergence. At least in this way. When do these averages converge in L2? So here T is the multiplicative action, like in the previous. And essentially this question, so let me write it as a ratio of polynomials. And essentially this question is equivalent morally, not even morally, but equivalent to understanding these type of correlations. When do these averages converge? And of course, if I take f to be complex valued function, that there is this n to the IT problems. So let's suppose that this action is actually finitely generated. Then this is equivalent to questions of for which finitely supported, let's say function plus minus one, such averages converge. And this theorem that these two theorems actually can be made into one, which would say that P, so this question has been studied like in some forums, like by Joel and collaborators, I guess. By also the pointwise convergence, I guess, for this ergodic, for this multiplicative actions was studied when you put T to the omega n, where omega is the number of prime factors. The pointwise convergence was studied by Florian Bergelsson. And so the question is like, when do these averages exist? And this theorem tells you that if P and Q are quadratic, if P times Q is product of linears, and one quadratic, and exactly one quadratic, then it's good for convergence. But actually, so you might expect that this holds for, say, other forms of higher degree. But actually, I will put it as a speculation, but the Chorley conjecture doesn't hold for any degree. Or these averages do not exist if degree P or degree Q is bigger or equal than 3. These averages do not converge. And this is so, for instance, you can cook up the functions f, which are both aperiodic and or pretentious, such that these averages will not have a mean value, even for simple polynomials.
Because polynomials are too sparse, but the values.
Well, but your average, they are, but so let me just explain. So these averages, for instance, would not go to 0 for f aperiodic. And it doesn't mean that these averages are not good for the recurrence. So these patterns are not good for the recurrence, because the way how we prove it, this is just taking these averages. So they still might be, these patterns might be partition regular, but at least this approach of going through averages is not right. So let me just explain one thing. So if you want to take something from that. This is the issue of large primes, which you are lucky in the case of quadratic polynomials. So no, that doesn't convert. So let me just. Oh, I don't have time.
Well, how long does it take?
So let me just like say the model thing. 1 minute. Just for those. So if you take a polynomials of the form say n squared plus 1, then these polynomials, there is many numbers which have a largest prime factor much bigger than x, say x log x, n log n. So there is many values here, positive. In fact, there is a positive proportion of that. So there is many of these terms that have a large prime factor, which is bigger than n, and you have full flexibility to rotate your averages on these large primes. So it doesn't really, if you put here m squared, our theorems, for instance, they do have the mean values. So once you average over 2 parameters, this issue disappears. But this is because these quadratic things are the norm forms. So you have equidistribution modulo large primes. However, if you put like forms of higher degree, one can show, at least assuming conjectures, that you can have enough primes to actually wiggle your average. So, and that means that these approaches for partition regularity would be quite difficult, and one has to be cautious about formulating conjectures about type of choice. Anyways, I'll stop here.